Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi. So I guess we realized pretty late that maybe the talk order should have been reversed. So I'm going to talk more about MLNs, I guess more from a slightly more sort of in terms of what they actually mean, how do you really model the problem and things like that. So this is I guess a little bit different from unlike previous talks. So I'm going to present a bunch of works that I've done during my PhD and later. Of course I'll talk a little bit about the current work that we are working some of the problems that we are focusing at i.i.d. Delhi. But this talk is meant more as an overview. Hopefully many of you might not have seen sort of the overall structure of MLNs and why we really need this kind of framework. So this is I guess joint work with my advisor at University of Washington, some work I did at UT Austin, and also then current work at i.i.d. Delhi. So here is a brief overview. I'll give some motivation for why you really do you need things like MLNs, and hopefully Rajiv's talk might have already given some motivation from an application perspective. But even just from pure machine learning perspective, why do we need something like MLNs? I'll define Markov logic more formally. I'll talk about inference and learning algorithms. So I'll address I guess some of the points that were raised in the previous talk. How do you really deal with structure that is inherent in the model? A couple of applications which will illustrate some of these ideas, and then finally some of the future directions that you could take. So I guess the motivation is that if you think about traditional machine learning setting, it typically assumes i.i.d. data, right? Identically independently distributed data. So you have the setting where you have pairs x, y. Of course there is last few years have seen a lot of work on structured output prediction, but traditional machine learning setting is where you have xy pairs, and each xy pair is assumed to be independent of the other xy pair. And the way to think about is that you have, let's say, one object, and you're looking for, let's say, maybe in a classification problem, particular class, and you have attributes for the object, and given those attributes, essentially you want to figure out what class the object might belong to. But if you think about real world applications, none of these assumptions is true. Data is not identically distributed, and the examples are no longer independent of each other, right? So in general, for many real world applications, you have multiple types of objects, and there are relations between those objects. So how do you really capture that? And that's sort of the motivating point here. So give you more concrete example. Think about social networking domain, and let's say you have people and you're trying to find out whether they have cancer or they don't have cancer. And you could have multiple attributes. Let's say you know whether they smoke or not smoke, maybe you know their age, gender, demographic background, and so on. So those could be their attributes, right? And then you could have rules, or you could have essentially things which would say that smoking leads to cancer. Similarly, you could have other attributes, and together they will determine the value of what is the value of cancer, whether cancer is equal to true or false for a particular person. But what happens is that many social network analysts have realized that the problem is not that simple, because essentially whether you smoke or not smoke depends on who you are friends with, right? So friendship determines smoking habits. In particular, if you're friends with someone who smokes, then you're more likely to be smoking. So already you can see there is sort of inherent structure here which cannot be clearly handled by making i.i.d. assumption, right? So we really want to be able to handle these kind of complex dependencies using our model, and we have to go to something which is more general in that sense, and that's where MLNs come. And if you think about various applications, and again Rajiv has talked about one particular application in the previous talk, but if you think about web search in general, information extraction we looked at, NLP, perception, medical diagnosis, all these applications, there is a very rich context, right? And really things depend on what context you are in. For example, social networking I already talked about. If you think about NLP, so just the fact that where certain words appear in what context a certain sentence is being said, that really makes a difference. I actually remember, I think Ray Mooney mentions in his NLP class that earlier NLP systems, the way they used to work was that they would translate from one language to another and back. And they were trying to test an NLP system from English to Russian and back. So they had this phrase which was out of sight and out of mind. And how would you translate it? So the system came up with the answer invisible idiot, So you can see that if you were to translate out of sight, which is fine, invisible, and out of mind is idiot, right? But when you have it together, it has a completely different meaning, right? So the context is very, very important, and this kind of dependency becomes very, very important, and that's where models like MLN come into picture. So in general, this area last 10 years has seen a lot of progress. This area is called statistical relational learning. And why this name? Because essentially, I guess I'm motivated enough that real worlds, if you think about real world problems, they are characterized by entities and relationships and uncertain behavior, right? So the first one is essentially traditionally more AI based systems like Horn clauses, first order logic. So they are typically relational models. You have rules and then you can define very rich relational structure. On the other side, if you think about machine learning models, in particular here we'll talk about Markov networks, Bayesian networks, graphical models, they have explicit notion of uncertainty. But unfortunately, there is no explicit way to capture this sort of rich template-like structure. So what we want is that we want to combine these two. In this area, actually, there are many, many different models that have come up in last 10 years or so. There is a book by Lise Guitour and Ben Tesker, which really gives a very good overview of all these models. But here, I'll talk in particular about MLNs or Markov logic networks, which are one particular model which combine Markov networks in terms of a statistical model with first order logic. So I guess there was a question about MLNs being finite. So it is true that in the current talk, I will assume that they are dealing with finite first order logic. So in that sense, they can be reduced to propositional logic, but note that still there is a template structure which propositional logic really loses, and we'll actually use the structure for efficient inference and learning. So that becomes very important. Having said that, there is some work that I worked that I did a while back where we extend them to actually sort of full generality first order logic, but I won't talk about that here. So I guess definition, maybe I can go a little bit quicker on that because that was already covered, but just for the sake of completeness. So actually before that, so let me give a little bit background. As I said, they combine Markov networks and first order logic. So Markov networks are undirected graphical models of data. So here nodes, you can assume for now they are binary. In general, you can have any kind of values, discrete values, or even continuous valued nodes, but for MLNs, we'll assume them binary valued. So an edge in the graph essentially depends that a node directly depends on its neighbors, right? What it means is that given all the neighbors of a node, it is independent of everything else in the graph. So that is sort of the semantics that a Markov network carries. And how do I define the distribution? The distribution is defined using a log linear model where you have exponential of the weighted sum of feature functions. So a feature is defined over cliques in the graph, right? So that is sort of intuitive because edges represent dependencies. In general, you would have a feature for any clique in the graph. It is sufficient to have features over maximal cliques in the graph. And we will deal with binary features, but again in generality you could have arbitrary features. So here you could define a feature which is on or which is 1 for particular states of the nodes in the clique. For example, consider the clique linking smoking and cancer. So for the states which satisfy the formula smoking implies cancer or not smoking or cancer, whenever any state which satisfies this formula, the feature is on, which means that feature takes a value of 1, otherwise it is 0. So already you can see how this is capturing the notion of when this formula is satisfied or not satisfied, and then the weight captures the strength of the feature, and Z is simply the normalization constant. So in summary, the probability of X, that is an assignment of 0 or 1 values to the nodes in the graph, is given by this formula. So that is essentially the distribution defined by this Markov network. This is also essentially a Markov random field if you look at sort of the mathematical description of it. Okay, so the other side, coming more from a relational learning side, what we need is first order logic. As I said, maybe more so finite first order logic. So we have constants, variables, functions, and predicates. For example, you could have Anna, which is a constant, X is a variable, mother of X, which is a function, friends XY is a predicate, defines a relation which takes value 0 or 1. Grounding corresponds to replacing all the variables by constants. For example, friends Anna Bob could be one grounding, friends Bob Anna, which is different from friends Anna Bob, is another grounding, and so on. So these are called ground atoms. Formulas are predicates connected by operators. So you could have smokes X implies cancer X, which is equivalent to not smokes X or cancer X. So this is just a logical formula. So I should caution that please don't think, you should make sure that don't think in terms of a causal relationship. They are purely undirected graphical models. So there is no notion of causality here. This is just a logical formula which takes true value for certain states and false otherwise. A knowledge base is a set of formulas essentially over these predicates. and a world corresponds to assignment of truth values to all the ground formulas. So that is just pure basic first order logic. So now, given this background, what is essentially Markov logic or Markov logic networks? So the intuition is that we want to make these constraints softer, right? In the motivating example that I gave, that smoking leads to cancer, it may not always be true. That you know that it's a very useful piece of information, but smoking may not always lead to cancer. So how do you really make these constraints softer? And that is the idea. And what we do is that we give weights to each formula logic theory, and the weight tells you how strong that constraint is. Higher the weight, more stronger that constraint is. If you have a zero weight, which means that essentially that constraint is not really relevant. And what is the distribution? So as we will see, the probability of a particular world or assignment of 0 or 1 values to ground atoms is now proportional to exponential of weights of the formulas that the theory satisfies. So I guess it will become hopefully become clearer when I have an example, but some of you can already see the connection with sort of the formulation that I had for Markov networks, right? It is going almost to the same kind of mathematical formulation. So before I go to the example, very formally, a Markov logic network is a set of pairs f and w, where f is a formula in first order logic. So here, as I said, this is finite first order logic, at least in this talk. W is a real number, so very little change from just first order logic. And given a finite set of constants, it defines a Markov network. So given formulas f and weight w for each formula, and given a set of constants, we can define a Markov network where for each ground atom there is a node in the graph, and for each ground formula there is a feature in the graph. Right, so that is how we will construct the MLN network or Markov network. So here is a concrete example, same example that I started with. So this is pure first order logic. Smoking leads to cancer. For all x, smokes x implies cancer x. And the second formula says that if x and y are friends and x smokes, then y also is smoking. And these are hard formulas. So now we give weights, which makes them softer. Right. So this is an MLN now. Given constants Anna and Bob, how would I create the ground Markov network? So I will create nodes for every ground atom. So smokes Anna, cancer Anna, smokes Bob, cancer Bob. And similarly, I'll have friends Anna Bob, friends Anna Anna, and so on. So note that this is a purely mechanical process, right? So I'm not doing anything magical here. I'm just taking formulas, substituting the constants for every variable, every possible combination, and then I'm creating this ground Markov network. Note that in general the variables could be typed, so you would substitute the typed constants for the particular variable. So these are the nodes in the graph. Now what are the edges or what are the cliques? So for every ground formula you create a clique. So smokes Anna and cancer Anna are linked through the corresponding ground formula. Similarly, smokes Bob and cancer Bob, so you link them by these edges. Similarly, for the second formula, you create the corresponding cliques. So note that the second formula has 3 predicates, which mean that you'll create 3-way cliques in the graph. So this is your complete graph corresponding to this MLN theory, right? So what I've done is I've simply taken the first order logic formulation, and in fact I even use the weights as of now, but we'll see where to use the weights. Right, so I've taken the first order logic formulation, given the constants, I create this network, and this is now a Markov network. As we will see, we'll define the features of this using the weights, and then you can do inference and learning over those. Right, so that is the connection between sort of the MLN theory and purely statistical model like a Markov network. So a particular assignment corresponds to coloring the nodes here, let's say 0 and 1, so green could be 0 and orange could be 1, and a joint distribution would specify what is the probability of this particular assignment of values to the nodes in the graph. Right, so given this, you can see that MLN Markov logic network can be seen as a template for constructing these ground Markov networks. Right, so you have these formulas which are the templates, and for different values of constants you will create different networks essentially. And what is the probability of particular world or assignment of values 0 and 1 to the ground atoms? This is given by this formula. This is exactly the Markov network formula. The features correspond to ground formulas now, and the weights essentially are determined by the MLN weights of the formulas. For every ground formula I have a feature, and then I substitute the weights and I get this expression. So note that the kth feature is on. As I said, we are dealing with binary features, so it will be 1 when the corresponding formula is satisfied. So for the states when the formula is satisfied, the feature will be 1, it will be 0 otherwise, and the weight of course comes from the first order logic formula. Now this is equivalent to this new formulation, which is the last equation here. What I have done is that note that the Wk is same across all the groundings of the same formula. So what I am doing is that I am adding up weights for a particular first order logic formula as many groundings are true. So Fkx is true whenever the formula is satisfied, right? So what I am doing is that I am adding up the weight Wi as many times as many are the true groundings of that first order logic formula, right? So I can actually have this second equation where the summation now in the exponent is over all the MLN formulas, that is first order logic formulas, and Wi multiplied by the number of true groundings of that formula, and that is essentially the distribution defined by an MLN in this formulation. So we'll be dealing with this equation. Yeah.
K belongs to ground formulas, but this necessarily may not form a clique, right? In a Markov network. So if you go back to your Markov network,
yeah.
So here, so smokes A, B, BA, friends BA, this forms a clique, right?
Yes.
So that would be one of the potential function in your Markov.
Yes.
Network, but this is not what the other formula is saying, right?
Smokes A, smokes B, friends BA, that one.
Yeah, A, B, and friends BA. So that's a clique, right?
A, B, friends, B, A. Yes, okay, sure.
Yeah, so if you go to the formula, the next page. So here when you say K belongs to ground formulas,
yes.
That's not a...
There is a ground formula, right? You substitute X for A and Y for B. So you get corresponding ground formula.
Oh, okay.
Yeah, so there is a one-to-one correspondence between those. Yeah. Yeah. So we get this formulation and we'll deal with this equation here. So I have talked about that, we want to combine statistical and relational models. So what is the relationship between statistical models and the MLN framework that I have given? So you can show that Markov networks, Markov random fields, Bayesian networks, log linear models. So all these models are essentially the special cases. So when I say special cases, what I am saying is that any distribution that can be represented by these can equivalently be represented by an MLN network in the way I have defined them. And I think the reduction is not very hard. For example, Markov networks is pretty straightforward, and even others you can show. In particular, note that they can be obtained by making all your predicates zero arity, because these are essentially propositional models in some sense. So once you have predicates without any variables in them, you will get one of these models depending on your structure, right? So you could encode HMM, you could encode a CRF using MLNs. But what MLN buys you is that there is a very rich relational or template structure that we'll exploit later that actually they are able to encode, right? So that is something that essentially buys all these traditional statistical models. So what is the relationship to first order logic? So you can show that in the limit of all the weights tending to infinity, essentially it reduces to first order logic, right? So weight tending to infinity becomes hard constraints, which means that it is essentially first order logic, and you can formally show that by taking the limit of all the weights tending to infinity. But what is more interesting is that suppose your weights are finite and you have a satisfiable knowledge base, which means that there is an assignment which will satisfy all the formulas, then that particular assignment or those assignments become modes of the distribution, right? So what we have done here is that we have kept, we still preserve the notion that assignments which satisfy maximum number of formulas will have maximum probability, but instead of having sort of 0 and 1 probability distribution like in first order logic, we have this sort of smooth decay. As you gradually dissatisfy formulas, your probability goes down and down like that, but still the modes of the distribution are exactly those assignments which satisfy maximum number of formulas or all the formulas if such an assignment exists. And here from the sort of relational setting, what have we bought here is that Markov logic is able to allow contradictions between formulas, which is very important for many sort of real world applications, right? So I guess this is the definition, and hopefully I have given enough motivation why this might be important and how do we combine first order logic and Markov networks. So I'll talk about inference and learning, and here we will see why or how the template structure in fact is useful for efficient inference. So the inference problem, I guess there are two different ways to look at it. So one is the problem of marginal inference, where given, let's say, green nodes, the value of green nodes, you are interested in finding the marginal probability of each node in the graph. So you could ask the question that given the green nodes, what is the probability of Smokes Bob being equal to 1, right? And there is also this MP inference task that was in the previous talk, where you are interested in finding the overall state of all the unknown nodes together. What is the most likely assignment to the nodes of which are unknown? right? So we'll look at more at marginal inference tasks, but I think the idea is easily generalized to the MP inference also. So putting it back into the formula, it's very simple. There are query nodes and evidence nodes, right? So evidence nodes are which are known, whose values is known, and query is essentially that you want to assign a particular probability to, and you just substitute back into the expression. Note that z now depends on x because x is fixed now, so your normalization constant will depend on the particular evidence values, and this is your expression that you have. And in general, this is a pretty hard problem because exact inference would require you to do something like a variable elimination over the corresponding Markov network, where the inference time or inference is exponential in the tree width of the graph, right? So which typically is intractable. So people have used various approximation algorithms, be it message passing like belief propagation, Gibbs sampling, or variational methods. So here we will talk about belief propagation. And this is standard sort of Markov network inference as of now, right? So we have the Markov network and we create this bipartite node network of nodes and features, where nodes correspond to ground atoms in our case and features are ground clauses, and we pass messages from nodes to features and vice versa. There are different initialization schemes. Let's say we initialize the messages to 1, and we know that the marginals are approximations, the messages are approximations to node marginals, and we know that whenever the graph, factor graph is a tree, then this gives you the exact answer. Otherwise there are no guarantees, but it is shown that this works very well in practice. So this is more graphically demonstrated. So you have smokes of just an example. So nodes on one side and features on the other side, and note that any node is connected to a feature if it appears in the corresponding ground clause, right? So I've just created this factor graph, and I can pass messages from nodes to features and vice versa. So I'll not go in the details of messages. Again, this is standard belief propagation formulation, where you pass these messages around and essentially you detect convergence. If it is a tree, then you know it will converge. Otherwise you sort of have a convergence threshold, and then you essentially get your marginals, approximation to node marginals. But now, so far so good. But the question is that that there is one message that we are passing for each variable and feature pair, right? So which is okay for finite, maybe bounded size graphs. But when we are dealing with MLNs, which are very expressive models, right? Suddenly the model could blow up, right? So for example, if you have transitivity constraints, just like in the previous talk, suddenly just having a variable with 1000 constants means you have billion features, right? So which essentially blows up very fast. Right? Although you may feel that, oh, you have a very compact model, but when you come to inference and grounding, the whole network will really blow up things. So you have to do something smarter. So here the idea that we use or we exploit is that there is a very rich inherent structure that your network is constructed from, that is the template structure given by the formulas. So maybe there is some information that essentially could be used to reduce the number of messages that are being passed from nodes to features. And what is that intuition? So this is the same graph that I constructed on the previous slide. So now given this graph, so if I could identify nodes and features on the two sides of the graph which are connected in exactly the same way to the nodes and features on the other side, and of course there are notions. What is this notion of there is a formal notion of what this means to be connected in exactly the same way, but intuitively you can see, because BP, belief propagation, is a local message passing algorithm, essentially what really matters here is that are you connected, what kind of nodes are you connected on the other side, right? So in this case, as you can see, the nodes in a particular box on the left side and as well as on the right side, they are connected to the nodes of similar kind in exactly the same way, right? So there are exactly the same number of edges, which means that you can actually replace this multitude of edges by a single edge between each cluster, right? And we show in our paper that doing BP over this, we call it lifted network, because you have lifted the network. Doing BP over this network essentially gives you exactly the same results as ground BP. So there is no difference mathematically, analytically rather. You can show that it gives you exactly the same results. The only change that you have to make in the belief propagation algorithm is these two constants, which essentially represent the fact that each edge now has underlying many messages which are being passed, right? But instead of passing n square messages, you are passing here k square messages, where k is the number of clusters. So less the number of clusters, faster this algorithm is, right? And just to give you a very quick intuition why this might be possible, so think of a social network where you have 1,000 or maybe maybe even more, let's say 1,000 people, and you have no information about whatsoever about any particular person. So what you can say about at the outset is that whatever the probability of smokes x, right, for any value of x, it's going to be the same for y, right? Because there is no way to distinguish between Anna and Bob unless there is a piece of evidence about one of them. Then they will have the same probability, which means they can be clustered together, right? Similarly, let's say you know that smokes Anna is true, then you can cluster Anna in one cluster, and then everyone else could be clustered together. So that is the basic intuition, and then we give the exact formal algorithm. Of course, in the degenerate case, it will boil down to the ground network, but we show that in practice it does work very well. The clusters are not degenerate. So this is lifted belief propagation. So hopefully this really convinces you that MLNs are not just a representational gimmick in the sense of you have more compact representation, but that compact representation actually buys you more efficient inference algorithm also, right? So which is very important for any real world application. So coming to learning, what does learning correspond to? The parameters of the model are the weights that you have. Of course you can learn the structure, but I'm not going to talk about those. So given the formulas, that is the structure of the network, you want to learn the weights. And your training data comes in the form of a relational database here. So you know who smokes and who has cancer and friends who are friends with whom. Typically for many domains that you work with, you make closed world assumption that is most anything not in the database is false. Of course you can relax that assumption, but then you have to use EM. So given this assumption, you can use standard ML maximum likelihood estimation. Given the training data, you want to find the parameters which maximize the likelihood of your data. So you can use standard gradient ascent approach. So here is the expression for partial derivative with respect to ith weight, and this is very intuitive, right? So what it is saying is that the partial derivative with respect to ith weight is difference between true number of groundings in the data of the ith formula minus expected number of groundings of ith formula according to the current model, right? So when partial derivative becomes 0, we know that we have reached the local maxima, and that again is very intuitive because your expected number of groundings equals the true number of groundings. But another key factor to note here is that to calculate the expected number of groundings, you have to do inference again. So inference in these kind of models is a sub-step of, the inference is a sub-step of learning. Every iteration of learning you would need to do inference, and again for inference you can use the techniques that I described for efficient inference, right? So even for learning you can in principle use the template structure to do efficient inference and then put it back into the learning iteration, and that's how you will do the gradient ascent approach here. So I guess the same thing here, same formula, just written again. Right, so this was about inference and learning, and finally I'll talk about a couple of applications which again will demonstrate the ideas more concretely. So I should mention that there are a number of applications that people have put MLNs to use across different places in US, other places, and I guess the list keeps growing. But I'll talk about entity resolution and a little bit about social network analysis that we have started to look at now at i.i.d. So entity resolution problem, so this is a very well-known problem, comes more from sort of the database literature. So the problem is that given a set of records, you want to identify which records refer to the same underlying entity, right? So here I have taken the database. So you assume that that you are given various attributes. For example, your citations have been segmented into authors, titles, and venue fields. But given that information, you want to figure out which of the citations refer to the same underlying paper, right? So given these records, intuitively, if you look at the example carefully, you may be able to say that the first two citations are probably the same paper, and then the second two citations are the same paper, right? And that is the task that we want to solve here. So these arrows essentially demonstrate if you were to do it correctly, that is how you will map various authors to each other, right? Author, title, and venue. Typically the traditional setting for this has been to use a model like logistic regression. And what are the features? The features are typically similarity scores between different attributes, right? The similarity score between authors, titles, and venues. Those could be essentially your features, and then you have sort of a class value of 0 or 1 depending on whether it's a match or not match. right? So let's assume that you use that kind of approach. So what will happen, let's say if you look at the first pair of records, then maybe the authors look similar. Of course, one of the names is abbreviated, but you could say that Parag Singla and P. Singla are the same author, similarly P. Domingos and Pedro Domingos. The titles look the same, venues are of course abbreviated, but maybe the threshold is high enough, or the similarity score is high enough to declare it as a match. Right? Similarly, you could go to the second pair, but second pair is more noisy, the third and the fourth citations, because even the title, there is a lot of text missing in the fourth case, right? So maybe you will declare it as a non-match. So that would happen if you were to do it independently. But when you try to do it in a collective way, when you do not assume that the pair match decisions are independent, then you can realize that AAAI 2006 and Proceedings of the 21st National Conference on Artificial Intelligence, that pair of venues in the first two records is exactly the same as the pair of venues in the third and fourth pair. Right? So once you are able to declare the first one as a match, you could glean that information to declare the second one as a match. Right? Of course, in general, in the collective inference setting, it will happen in a collective way, and the information will flow both ways. But I'm just trying to demonstrate how doing it in a collective way by taking this dependency into account will really help you make a better prediction. So in terms of MLN, I guess I will not go in complete detail. You can write the predicates, you can write the formulas. One very interesting thing or nice thing is that each formula essentially implements one of your sort of traditional models. For example, the second formula here is essentially implementing logistic regression, because what you are saying is that for every word that two fields have in common, then essentially you are saying that their records are the same. So every other word, remember the second formula will be true for every word they have in common. So if they have three words in common, it will fire 3 times, right? So that is essentially your feature value, and the weight of the feature is essentially weight of the formula, and this essentially implements logistic regression, right? So in terms of coding or implementation exercise, this makes things very simple. At the same time, you can have more formulas which implement collective classification of the kind that I told about. Similarly, you could have things like transitivity, which again a traditional model will not allow, right? So not only it buys you representational power, not only efficient inference and learning, but also this kind of seamless way of trying and testing various features, writing these formulas for these kind of problems. So finally, briefly, I'll talk about large social network analysis, a problem that we have started to look at now. In particular, we are looking at Twitter and maybe some other data sets that we are trying to get hold on. And there are different problems that we are looking at, but one particular problem I want to mention here. So think about, let's say there's this Twitter network, and of course it is a directed graph, but here I've shown undirected. So there's this person in the middle, and he has various friends whom he follows, and they tweet about various topics. Right? And those of us, I guess, who have been following cricket, they know that I think last year there was this news about Sachin Tendulkar scoring century of centuries, and that became a big news, right? So now what we are looking at is that let's say this person, a lot of people in his network tweet about this topic, that Sachin Tendulkar is going to go score century of centuries, and he also tweets about that particular topic. Now the problem that we are looking at is called the attribution problem. That is, we want to answer the question whether this person tweeted about this topic because he has inherent interest in this topic, or is it more because all his friends are tweeting and that's why this person really tweeted about this topic. And you can see there is a very interesting difference between those two, because if this person had inherent interest, then it's a regular event in the Twitter network and probably not something big is happening. But if this is more because of attribution, because of his followers are essentially the persons he follows, they are tweeting and that's why he is tweeting. And if there are many such events happening in the network, then hopefully you can predict that this topic is going to go viral. Right? So of course this work is more still in the basic preliminary stage, but here hopefully we hope to be able to use MLNs, because you can see there is a complex dependency structure, how you tweet and how your tweeting behavior might depend on people you follow and so on, and then may be able to predict this kind of attribution problem by predicting these low probability events in the network graph. So other feature directions that I've been looking at with some of my students, one is approximate lifting. I've done some work on where you want to identify clusters approximately. So remember, the lifted belief propagation identified clusters exactly, but maybe you want to allow some kind of approximation, you get better clusters, but then performance may deteriorate. Similarly, there is another, I guess another direction is learning with partial observability. For example, I mentioned about EM, but as it turns out that because you're dealing with undirected models, the M step is pretty hard, even if you have the full training data, right? So maybe, as it turns out that using EM versus doing a direct gradient ascent might be comparable with each other. So we are doing some experiments on that. Dynamic MLNs is where there is this notion of time. So the social network example, there is this explicit notion of time, and of course you could put it in the MLN as a new variable, but of course you know that the time sort of flows linearly, and you could exploit that, and then you could essentially come up with a dynamic MLN formulation that we are currently looking at. So to conclude the talk, real world is characterized for many problems, if not all. The data is non-i.i.d. There are entities and relations between objects and relationship between them. There is uncertain behavior, and we want to capture the both. This whole area of statistical relational learning which has come about, and MLN is one such model which tries to capture both of these aspects by having weights to real world formulas, which essentially become templates for constructing round Markov networks. And I talked about a couple of applications to motivate why they might be useful. Thanks. Yeah. Right. So that's a good question. So there is this notion of uncertainty, but they are Bayesian in the sense that there is no degree of truth here. So if I understand correctly, in fuzzy logic you have the degree of truth, right? But here this is Bayesian in the sense that the truth is fixed, right? It's 0 or 1. It's about your belief. So in that sense, it's different from that. Yeah.
Can I ask what are the approaches you're taking for approximate drifting?
Right. Yeah. So one approach is very simple. That essentially what you do is that so I guess I did not go in detail, but the way it works is that it starts with maximal clusters. So you will have a cluster for every predicate, and then you split it as you see the messages being different. Right. So what you can do simply is that you can cut the splitting off at certain point and declare your clusters that these are your real clusters. So that is something that we looked at, and that performs fairly well for certain vision problems. Right. For certain denoising problems, you can show that if you run the full sort of lifted algorithm, then it leads to degenerate clusters. But doing splitting only at 3 levels give almost the same results, and then it is much more efficient. Right. So that's, I guess, the basic idea.
Do you have any theoretical learning that okay, if you cut off at this point, you are guaranteed to?
Right. So yes, that's a good question. So we have workshop paper where we do show some guarantees, but I think the bounds are not very tight. Yeah. Although we do show that the marginals are within the actual marginals. So note that when I say actual marginals, they are the marginals BP, right. So that is the best guarantee that we can give. How far or close is it to the actual ground BP? And we do have some guarantees on that. Yeah. Thanks.